this lecture we are going to conclude our discussion on introduction, and so in this lecture I will first describe what is the difference between block codes and convolutional codes, and then we will talk about some very simple decoding strategies, and finally we will explain what we mean by forward error correction, automatic repeat request and hybrid ARQ. So as I said, we will first describe, so error correcting codes can be broadly classified into two classes, block codes and convolutional codes. We will describe what is meant by block code and what is meant by convolutional code, and we will bring out a difference and similarities between the two. Then we will talk about various decoding strategies, and finally we will talk about what we mean by forward error correction, hybrid ARQ and automatic repeat request. So we will start with what is block codes. So as the name suggests, in block codes we take a block of k bits and map it to an n bit code word. So our information sequence is parsed into blocks of k bits, and we take this block of k bits and map it to a block of n bits. So we denote our information sequence by u. So this is a k bit sequence, u0, u1 to uk minus 1, and our encoder is going to map this k bits into an n bit sequence, which is denoted by v. Now in block codes the encoder is memoryless. What do we mean by that? So when we encode a block of k bits, our output depends only on that current block of k bits. It does not depend on what were the previous blocks of data. It only depends, output only depends on the current k bits. So that is one property of block codes which makes it different from convolutional codes. Block codes are memoryless. As we mentioned in the previous lectures, we define our code rate to be the ratio of number of information bits to number of coded bits. So the ratio of information bits to coded bit is basically will be denoted by code rate, and is typically denoted by R. K is number of information bits, n is the number of coded bits. So n minus k is number of redundant bits that we are adding to our information bits, and these are also known as parity bits. If we are considering without loss of generality, we will basically consider in these set of lectures binary code words. So our information sequence consists of zeros and ones. Similarly, our code sequence also consists of zeros and ones. Since we are considering a block of k bits and binary code words, so number of code words is basically 2 raised to power k. So a binary nk block code consists of 2k code words, each of length n. Now these code words need not be binary, however it is the same theory mostly applies to non-binary code words as well. So we will restrict our discussion to binary code words. So let us consider an example of a linear block code. So in this example, our number of information bits is 3, the number of coded bits is 6. So the code rate, which is ratio of number of information bits to number of coded bits, is 3 by 6, which is half. So what we have here is basically our message bits. Now k is 3, that means there are 2 raised to power 3, which is 8 code words, and these are basically from 000 to 111, these are the 8 code words. Now the message, these are the 8 message bits, and corresponding to these message bits, these are the 8 code words. Now 000 is mapped to all 0 sequence, 100 is mapped to 011100, likewise other sequences have been mapped. So, let us look at how we have mapped, how have we found out the message parity bits for this particular code word. So, let us look at each of the columns of these code words. So, let us look at this column first, which is 00001111. So, how was this column, how did we map to get this column? If you look at information bits, this column is nothing but same as this information bit. You can see 00001111. Similarly, look at this one. This column is same as this column, 00110011, and this column is same as this column. So, in other words, this bit of the code word is same as this bit of the information sequence, this bit of the code word is same as this bit of the information sequence, this bit of the code word is same as this bit of the information sequence. Now, let us look at this one. So, if we do U XOR of these two, look at this, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0. We are talking about binary addition over binary field. So, 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0. It is modulo 2 addition. So, 1 plus 1 is 0, this is 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and 1 plus 1 is 0. So, if we let us say denote this by U0, U1, U2, and we denote these by V0, V1, V2, V3, V4 and V5, what we have found out so far is V5 is same as U2, V4 is same as U1, V3 is same as U0, and what is V2? V2 was U0 plus U1. Now, let us look at V1. If we look at these two, U0 plus U2. So, 0 plus 0 is 0, 1 plus 0 is 1, 0, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, 0 plus 1 is 1, and 1 plus 1 is 0. So, V1 is nothing but U0 plus U2. Okay. Now, let's look at last this one V0. What is V0? We can see that this is same as U1 plus U2. This is U1 plus U2. So, 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0, and 1 plus 1 is 0. So, this is how we have mapped our information bits into our coded bits. Okay. So, again to recap, in block codes we partition our information sequence into blocks of k bits, and we map these k bits into blocks of n bits, and this mapping is memoryless. In other words, how we map these k bits does not depend on how we have mapped the previous blocks of k bits. Okay. So, let us now contrast it with what are convolutional codes and how are they different from convolutional codes. So, in block codes we parse our information sequence into blocks of data and we handle them block by block. Whereas, in a convolutional code you can process your information sequence in a continuous fashion. The second difference is the encoding in convolutional code is with memory. In other words, the current output not only depends on current input, but it also depends on past inputs and outputs. Okay. So, unlike block codes, in convolutional codes the output depends on past inputs and outputs. So, if we have an nk convolutional codes where k is the number of information bits, n is the number of coded bits, we have another parameter which we are calling it memory order, which signifies basically how many past bits or how many, what is the past information that has been used to generate the current output. So, we define a convolutional code not only by these parameters n and k, but another parameter which basically denotes the memory of the encoder. Another subtle difference, in case of convolutional codes, typically the values of k and n are much smaller compared to values of k and n for block codes. So, let us take an example now of a convolutional code. So, here we have one input and two outputs. The input we are denoting by u of L, output we are denoting by v of L1, v of L2. Now, note here, each of the outputs here not only depends on the current input, which is u1, but it also depends on these past values. It also depends on what ul minus 1 was, what ul minus 2 was. So, this is an example of memory order 2. So, the current input, current output not only depends on current input, but also depends on past two values of the input. So, this is an example of a 2, 1, 2 convolutional code. N is 2, there are two outputs, k is 1, one input, and memory order is 2, because the output depends on past two values of information sequence. So, you can see here the first input, which is V1 VL1, it is basically UL plus UL minus 2. So, in other words, it depends on the current input and what was the input, past two values basically. And similarly, this one depends on current input, past input, one past input, and this UL minus 2. So, this is basically how. So, you can see the difference here. The output not only depends on current input, but it also depends on past inputs. Similarly, here basically you can see in a convolutional code the output depends on past inputs and outputs. Okay. So, that is one of the major difference between convolutional codes and block codes. Now, let us move to the topic of what sort of decoding strategy should we employ when we want to decode a code. So, now as I said, a decoder objective is, it takes as input the demodulated signal R, and it has to produce an estimate of the information sequence U hat, right. So, the decoder produces an estimate of the information sequence based on what it has received of demodulated output, which is R. Now, we can say this estimation of the information sequence problem is equivalent to estimating the code sequence, because there is one-to-one mapping from a particular code word to the information sequence. So, we can say equivalently the problem that decoder has to estimate is, it has to estimate the code sequence given a receive sequence R, because there is one-to-one mapping from the message bits to the code bits. So, what is a decoding strategy, or what is a decoding rule? A decoding rule is nothing but, given a receive sequence R, we are trying to estimate what our code sequence, transmit code sequence was. So, we are trying to estimate V hat or U hat from receive sequence R. So, we have to decide what rule or what logic should we use when we get receive sequence R. How do we assign that receive sequence R to any particular code word? Now, one of the policies which we can use is basically to minimize probability of error. Now, when does an error occur? When my decoded sequence is not same as my transmitted signal. So, my probability of error is given by probability then when my estimated sequence, which I denote by V hat, is not same as V. So, this can be written as probability of error given R receive sequence multiplied by probability of the receive sequence R and sum over all possible receive sequence. And error is nothing but when V is not same as V hat. So, I can write this equation in this particular form. So, if I want to minimize probability of error, I will have to minimize this. So, my decoding rule should be such that this is minimized. So, there are two terms in this, one is P of R and another is this term. Now, whatever V hat I choose, that does not change P of R. So, the choice of decoding rule does not change my P of R. So, in other words, if I have to minimize probability of error, I should choose my V hat in such a way such that this is minimized. For each receive sequence R, this term should be minimized. Okay. Now, minimizing this term is same as maximizing this term, correct. Minimizing the probability V hat is not same as V given R is equivalent to maximizing the probability that V hat is equal to V given R. Okay. So, we have to maximize this. Now, using base rule, we can write probability of V given R as probability of R given V multiplied by probability of V divided by probability of R, and this has to be maximized for every basically V. So, we should choose our V such that this thing is maximized. Now, again, choice of V does not change this. So, we can write our probability to to maximize this then becomes maximizing this quantity. So, we can say maximizing this is nothing but maximizing this quantity, because this quantity does not depend on choice of V. Okay. So, if we want to minimize probability of error, we want to maximize this, we want to maximize this quantity. and a map decoder, a maximum A posteriori probability decoder is the one which will do exactly that. So, it will choose a V hat such that this probability is maximized. Now, what happens if all code words are equally likely to happen? If all code words are equally likely to happen, then look at this term, probability of V will be same. So, in that case, maximizing probability of V given R is same as maximizing probability of R given V. So, that is what we are saying. If all code words are equally likely, then maximizing probability of V given R is same as maximizing this likelihood ratio, likelihood function P of R given V. So, a maximum likelihood decoder is the one which will choose V hat such that this quantity is maximized. Now, if we consider that our channel is discrete memoryless channel, in other words, we can write the probability for a discrete memoryless channel, we can write probability of received sequence R given transmit sequence V, we can write it as product of these individual probabilities. So, if that happens, then we can further simplify our maximizing criteria. So, we want to maximize this is same as maximizing this. Now, since log of x is a monotonously increasing function of x, we can say maximizing this probability is is equivalent to maximizing log of probability of R given V. Now, if we do that, then this product becomes summation. Okay. So, then we can basically write this as basically then log of probability of R given V will become basically summation, and this will be basically, of course, this will, there will be some log term here, and this is basically much easier to compute. Okay. So, let us take an example. We are interested in finding what would be the maximum likelihood decoding rule for a binary symmetric channel. Now, recall what is a binary symmetric channel? There are two inputs, let us say 0 and 1, two outputs 0 and 1 with probability 1 minus p. I receive my bits correctly and there is a crossover probability of p. Okay. So, the question I am asking is, if I have a code word of length n which is transmitted over a binary symmetric channel whose crossover probability is p, what should be my maximum likelihood decoding rule? So, how do I solve it? As we just saw in the previous slide, maximizing probability of R for maximum likelihood decoder, we have to maximize probability of R given V, which is equivalent to maximizing log of probability of R given V. So, let us try to compute what is the log of R given V. Okay. Now, before I calculate probability of R given V, let me introduce another term which is called Hamming distance. Now, what is Hamming distance between two code words? So, Hamming distance between two code words or two n tuples, let us call it Hamming distance between R and V, both are n bit vector basically. So, Hamming distance between R and V is defined as number of positions in which R and V are differing. So, for example, if let us say R is 1 1 1 0 1 1 and V is 0 1 1 1 0 1, then what is the Hamming distance? It is differing in the first location 1, it is not differing here, not differing here, it is differing here that is 2, is differing in this location, that is 3, it is not differing in this location. So, R and V differs in 3 locations, one is this location, other is this location, third is this location. So, the Hamming distance between R and V is 3 in this case. Okay. Now, when we are sending an n bit code word over a binary symmetric channel, what happens? Some of the bits will get flipped with probability crossover probability p. Let us denote those number of flip bits by d. So, Hamming distance between two R and V will specify the locations where R and V are not same, and when R and V is not same, that means those are locations where error have occurred. So, number of positions that got flipped as a result of sending this code word over binary symmetric channel, that is denoted by this d of R and V, and the remaining number of bits which did not get changed, that is basically n minus d R V. So, these many bits did not get changed and these many bits got flipped. So, what is the probability that d bits got flipped? That is given by p raised to power drv, and what is the probability that n minus d bits were received correctly? That is given by 1 minus p raised to the power this quantity. So, we can write probability of r given v as p raised to power d into 1 minus p raised to the power n minus d. Now, if we take log on both sides, then this will basically become n minus d log of 1 minus p plus d times log of p. Now, we take terms containing drv out. So, what we will get is drv log p by 1 minus p plus n times log of 1 minus p. So, to maximize this probability, we have to choose our v hat such that this is maximized. Now, look closely at both of these terms. Let us first look at this term. Does this term depend on selection of v? No, it depends on n, which is code word length, it depends on crossover probability p. So, whatever v we choose, it does not change this probability. So, in other words, to maximize this, then we will have to maximize this first term. Now, look at this term closely. Typically, the crossover probability will be smaller than half. If that happens, what happens to this ratio p by 1 minus p? This will be some ratio between 0 and 1. And what happens to log of a number which is between 0 and 1? That is a negative quantity. So, what we get then is, to maximize this, we have to maximize minus of drv, correct? So, a maximum likelihood decoder will choose a v such that minus of drv is maximized. In other words, we should choose a code word v in such a way such that drv is minimized. When drv is minimized, then only minus of drv will be maximized. So, that is what we are saying here. Log of p 1 minus p is less than 0. So, this will be a negative quantity. When you want to maximize a negative quantity, this term should be as small as possible, and this term does not depend on selection of V. So, this gives us a decoding maximum likelihood decoding rule for binary symmetric channel. And what is that? We should choose a V such that DRV is minimized. In other words, we should choose a code word V such that Hamming distance between the code word V and the received sequence is minimized, and that makes sense. And that is our maximum likelihood decoding rule. So, finally, I am going to conclude this lecture with definition of few error correcting strategies. The first one which I am going to describe is what is known as FEC, forward error correction. So, in systems where there is no feedback from the receiver to the transmitter, we are calling those systems as one way system, where transmission happens only in one direction from transmitter to receiver. In those systems, the error correcting codes that are used are known as FEC. So, when you hear this term FEC code, it basically means when we are sending, so this is the error correcting code used for when we are using transmission one way from transmitter to receiver. Now, in some cases, we have a mechanism of feedback from the receiver to back to the transmitter. So, in those cases where there exists a feedback from the receiver to transmitter, we are calling these systems as two-way systems. So, for these systems basically the error correcting strategy which is used is what is known as automated repeat request. Now, how does this works? So, you initially send some coded packets where you just use parity bits for error detection. So, you send your information bits and some few parity bits for error detection. At the receiver, using those parity bits, the receiver will try to judge whether there is any error in the received packet. If it finds that there are errors, it will send a negative acknowledgement, and again you will retransmit the same packet or some additional parity bits. So, that is basically same packet basically. So, that is your automatic repeat request scheme. Now, in this automatic repeat request scheme, the idea is you are sending an uncoded packet with some bits for error detection. So, you are not really sending any bits for error correction. So, this is typically useful if the links are very good. You just are sending uncoded packet with some bits for error detection, and occasionally when the packets are not received correctly, then you ask for retransmission. A strategy that combines both forward error correction and ARQ is known as hybrid ARQ system. In this, you send coded packets from transmitter to receiver. Now, if these coded packets are not received correctly by the receiver will basically send a negative acknowledgement, and then you will resend the same packet, or you will try to send some additional parity bits, and using those additional parity bits you will try to now decode the original packet. So, hybrid ARQ is a combination of forward error correcting scheme and automatic repeat request scheme. Typically, it is in a communication system you will see a combination of both forward error correcting schemes and hybrid ARQ scheme used. So, with this I am going to conclude this lecture. Thank you.